quantum algorithm, which is the Deutsch-Jozsa algorithm. Technically speaking, this is the one can call this the second quantum algorithm. The first algorithm is the Deutsch algorithm, which is a favorite of my PhD supervisor. He enjoys talking about the Deutsch problem because it explains the power of quantum computing in very simple terms. But we shall be talking about the Deutsch-Jozsa algorithm. So what is the Deutsch-Jozsa algorithm? So let me say I have a Boolean function f, which is defined from n variables to one variable. So I say this has n variables to one variable. Okay, so it takes an n variable input. This is the input side. Okay, there is a new question. The H3 part, I told you I'll explain during the demo, so don't worry. Then you'll understand what I meant by H3. And the reason I wrote H3 is I didn't want to use too much mathematics. So, if you need the accurate representation of it, I will write it maybe once the session is done. And I get one Boolean variable as the output. Now, f has n variables, so I know that there are did not change. So I know that there are 2 to the power n possible values of the output. Now, this is also a Boolean variable. So essentially, this quantity here is also going to be 0 or 1. Okay. So, and here I say 2 to the power n possible values of the output. Essentially, for each n-bit string input, I can get either a 0 or a 1. Okay, now what happens is the following. The Deutsch problem is this. Given, again, I'm not citing this from a textbook or the original paper. This is the effective, the simplified problem statement. Okay, given a function f and also given the information that f is either balanced or constant, either balanced or constant, how do we distinguish between the two? Essentially, my f is a constant function, meaning it is either all zeros or all ones. It is either that kind of a function, and a balanced function. A balanced function is a function that outputs 0 and 1, an equal number of times. So that is it. This is a balanced function. A constant function, I'm not writing the definition separately. I hope everybody understands that. If not, you can post a question in the forum and I will write it here. So now how do I distinguish between these two? I know the function is either balanced or constant. It cannot be anything else. So this is a very, contrived problem. This is not a real world problem. This is not, a problem that we will encounter in our day-to-day existence. But nonetheless, this illustrates the power of quantum computing. So now, where does quantum mechanics help us? Where does, quantum computing help us? So where it helps us, I should have duplicated this slide beforehand. You know what? Duplicate this guy. Yeah. So first, what we do is the following. Let me say I try to construct this value. I try to construct 1 minus 2 f of x. Let me call this value y. Y is equal to 1 minus 2 f of x. So this implies y is equal to 1. Or rather, I should write it like this. 1 if f of x is 0, and minus 1 if f of x is equal to 1. I hope you can see that, because 1 minus 2 times 0 is going to be 1, 1 minus 2 times 1 is going to be minus 1. So essentially, every time f of x is 0, I will have y is equal to 1. Every time f of x is 1, I will have y equal to minus 1. So I can actually say there is a one-to-one mapping between y and f of x. Like over here, I said 0 and 1. So I can now replace that by saying it is a function where y is plus 1 and minus 1 an equal number of times. And here, it is either y is always a constant. It is either always plus 1 or always minus 1. Okay. Now, therefore, this quantity y is equivalent to f of x. Now, let me define the object here. Oh, wonderful. Yes, the sticky lines are working. Yes. So I have this quantity called UF. Why am I calling it UF? Those who don't know, those who don't know, it's just assume that it's my favorite symbol. Now to this, I will pass essentially there are n bits input. Then what I will get on the outside is the same n bits. However, I will multiply them by y. So essentially, if I send x1, x2, all the way till xn, then on the outside, I'm going to get y times, okay, let me not say x vector, let me say y times x1, x2, x3, all the way till xn. Now this is what I call an oracle representation. Essentially, what is an oracle representation? An oracle representation is, I set the input and my oracle will give me back the same input and the output corresponding to that input. So this y we know is equivalent to f of x1, x2, xn. So it is an n-variable Boolean function. There are n input bits to it. That y is multiplied with this. Now, this is an oracle representation of a Boolean function. This is one way to represent a Boolean function. In fact, for most unknown Boolean functions, this is usually how we have the function with us. Unless and until you don't know the exact formula of the Boolean function, it is something that, like, there is something that is there. Now, what happens is when I move from this to the quantum side, and then I can, okay, yes, I shouldn't have written UF here. I will write F here. So this is the oracle representation of F. Now remember over here, where was it? Yes. I've said that it is possible to implement a Boolean function as a quantum gate. Now this is something that I've given. So what I'm going to do is just leverage that property. Okay. And I'm going to say on the quantum side, I will have a quantum oracle. Now, this is very important. In fact, to this day, I will say 99% of the quantum algorithms that are out there use only the quantum oracle model. There are precious few algorithms that try to deviate from the or approach problems in a different manner. So now I will define the object UF, which will again take n inputs, but this time it's going to take n qubits. So it will take n qubits and the output is again going to be the same as this. So let me say the state of this n qubits is given by ket x1, x2, all the way till xn. Then what I shall get is this quantity. I will get the output is going to be 1 minus 2 f of x, or rather f of x1, x2, xn, multiplied by ket x1, x2 till xn. I can write this better. It's completely illegible. So what I will get is 1 minus twice f of x1, x2, xn multiplied by this vector x1, x2, xn. So this is what I will get. Now remember, this is a quantum oracle. Now a quantum oracle is ultimately a quantum gate. And since this is a quantum gate, this is linear. Essentially, if I were to send, now the next part that I'm going to write is the only thing that all of us needs to understand. Once again, I should have duplicated the slide beforehand. Yeah, all right. So essentially, now you know what, let us stick to a smaller model. Let me say, instead of this, I will set n equal to 3 so that writing things will become easier. So, no, please don't make arrows. Yeah, so I have UF, and let me say n is equal to 3. So I have 3 inputs, x1, x2, or rather, let me not mention that here. And I will get whatever, how many ever inputs I have, I will have those many outputs. Okay. Now, if I were to send a state like this, x1, x2, x3 plus x1 dash, x2 dash, x3 dash, then what will I get on the output side? What will this give me? What will UF give me? UF is actually going to give me, you know what? I will equivalently write this as y of x over here. Instead of writing it as 1 minus 2 f of x, which is, slightly complicated to write. So what I will get is the following: y of x1, x2, x3 get x1, x2, x3 plus y of, oh, sorry. Oh, dash. It's for the dashes. X1 dash, X2 dash, X3 dash. So the linearity principle says that if I send the sum of two inputs, then this UF will act on each of them separately. I know for any X that comes in, I will get Y of that X. So by extending the principle of linearity, this is what I will get. Okay, now let us come back to this quantity here. Okay, and let me ask the following question. If I were to evaluate this quantity, sum of y of x, summed over all possible values of x, and let me say y is a balanced function. Let me say y is balanced. Balanced. Then what is this sum going to be? Y is going to be +1 and -1 an equal number of times. So when I perform this summation here, what's going to happen? If for every 1, I will have a -1. Therefore, this summation is going to be 0. And if y is constant, then what will this sum be? All y's are going to be +1 or all y's are going to be -1. So I will either have +2 to the power n or -2 to the power n. I hope you can see this. For a constant function, this summation will happen over and over and over again. So let me quickly take 1 second because I saw a relevant question. So let me just address that. Yeah, so first, Anusha has asked, can I explain why y is equivalent to x? Because see, every time f of x is 0, y of x is 1. Every time f of x is 1, y of x is -1. So there is a one-to-one correspondence. That is why it is equivalent. Like if I know the value of y, I know the value of f of x. If I know the value of f of x, I know the value of y. So this back and forth, this is perfectly invertible. Since this is an invertible map, I can use one in place of the other. Okay, so
Hi Jyoti, just 1 second. Sorry for interruption. Like we have limitation, like we told for 1 hour only. So I guess like for today we will finish like this Deutsch-Jozsa. I'll go. Then maybe on the upcoming Sunday we will cover rest of them if time permits.
Oh, sure.
Is it fine? Yeah.
Yeah.
We will extend this session half an hour more, like till 6:30. We will take this session. So guys, please stay and listen. Yeah.
So no, so for half an hour more, what do I do? Do I just answer questions or can I cover other things also?
If we can finish this first, then
okay.
Yeah, we will finish this. Then we will at maybe 5-10 minutes. We can take Q&A.
Sure. Okay. All right. I will take just 5 more minutes.
Yeah,
I know. Covering
like
3 entire quantum algorithms in one session is kind of difficult. I thought I can rush through it, but as I started explaining, I kind of got caught up.
No, it's really good. Like from basics, like what all gates are required. So yeah, it's really good. Yeah.
Okay. So all right. So see, another question I got from Mihir Rath is 1 minus 2 f of x is essentially a linear function. Why is it only this? Can be any linear function or linear combination. Yes, you're right. In fact, it need not even be just linear. There are many invertible maps that I have. As long as this mapping is invertible, I can use it. So it doesn't only have to be a linear function. A linear function, in fact, since you mentioned it, again, to people who are familiar with mathematics, I can write this as minus 1 to the power f of x also. Because when f of x is 0, I will have minus 1 to the power 0, which is plus 1. And when f of x is 1, I will have minus 1 to the power 1, which is minus 1. So a non-linear function, this is an exponential function. In fact, this is a complex valued function. A complex valued function will give me the same results as the linear function. So linearity is not required here. There are infinitely many ways to map this. And in the domain of Boolean functions, all of these mappings have different applications in different places. But for our present application, you see, every balanced function, if I take the sum, it is going to give me 0. Every constant function will either give me plus 2 to the power n or minus 2 to the power n, a function defined over n bits. Okay, so since that is the case, I can now use this information to distinguish. So this is how I distinguish between, so this is my distinction. So this right here is my distinction. Now, how does a quantum algorithm allow me to achieve this? Quantum algorithm allows us to achieve this through the following process. Essentially, see, if I add 2 of them, I will get 2 of these values in my output. What if I add all 8 of them? Then I will get all 8 possible values on the output. Now, how do I get all 8 of them? By applying this H3 operation. Okay. Now I will tell you what H3 means. Since I'm getting kind of an extension, I will quickly say what H3 means. So let me write this in black very quickly and very short. So I will apply Hadamard on the first, Hadamard on the second, and Hadamard on the third. And I told the state is ket 0, 0, 0. So each of these states are individually in ket 0. And to this, I will pass the UF, the quantum oracle. So then on the output, what I will get is this. I will get sigma x1, x2, x3 all equal to 0, 1. So this will give me 8 possible values. Y of x1, x2, x3 multiplied by ket x1, x2, x3. And remember, applying the Hadamard gave me a 1 over square root of 8 normalization constant, essentially the number from the normalization criteria. So I can write that over here, square root of it. So what have I done? By just using the quantum oracle one time, I have evaluated the Boolean function at all points. And how was I able to do it? Because of linearity. Every quantum implementation of a Boolean function is linear. It does not make the function linear, mind you. I have a linearized implementation wherein I can implement the function over every point using one query. This is something that, in more technically, worded places. Let me use a different color here. This whole thing is what many people refer to as quantum parallelism. So this is quantum parallelism, or people may call this superposition, where we have seen the word superposition before. So this is what people call superposition, and they say this is a quantum resource and whatnot. Or even more technical, like physics-oriented people might know this as coherence. All of these words refer to the same phenomena, same underlying phenomena, that is linearity. My quantum implementation of the Boolean function is a linear implementation. Since it is linear, I can pass multiple inputs to it in one go. Since I can pass multiple inputs through it in one go, all the outputs will be obtained here. Then, now just take my word for it. Once I have this, I can compute this sum in just one more step. So from here, and that one more step, what it is I will just apply 3 more Hadamard gates on this end. If I apply 3 more Hadamard gates on this end, then my output is going to be depending on these values. So what will happen is, if y was a constant, then the output state will become 0, 0, 0. If y was not a constant, if y was a balanced function, then the ket 0, 0, 0 state will never occur. So essentially what my Deutsch-Jozsa algorithm is doing is distinguishing between these two values of the sum for a constant and a balanced function. So since I have an extension, I will take a couple of minutes to talk about some things here. Okay, so I will duplicate this. I forgot that I can do this. We'll lasso this whole thing. Now remember, for me to develop my quantum algorithm, all I needed is the linearity of my quantum gates. That was the only thing that I needed. That is the only thing that I used. So the only quantum property used is the linearity of quantum gates. Okay, this is the only idea that I've used through and through. But remember that this property that we have here, I didn't use any quantum computing to derive this. This is a very classical result. In fact, this result was known for a long, long time. In fact, there is a classical algorithm to calculate these sums also. But remember what I told way back up here, the classical version of computing this particular process is actually of the order 2 to the power n. In fact, it is slightly above 2 to the power n. It has another factor. It has a factor of n attached to it. But David Deutsch and Richard Jozsa discovered that in quantum computing, the evaluation of sigma y, this quantity that I wanted, sigma y of x, can be done with a single quantum query. So what do I mean by a query? A query is how many times I call this oracle, how many times this oracle is introduced into the circuit. Okay, so over here, I just need the query once. And in fact, this is not only true for 3 variables, this is true for any number of variables. How many ever variables I have, set all of them to 0, apply a Hadamard to all of them, then apply UF, then apply a Hadamard to them again. That is the Deutsch-Jozsa algorithm. So, what we see here is this principle of linearity, ultimately that is what is giving us this speed up. Okay, whereas, so similarly, the same operation on the classical side requires 2 to the power n additions. Why 2 to the power n additions? Because there are 2 to the power n values of y. I cannot find the sum of some numbers without adding all the numbers. So this thing essentially where I have 2 to the power n summations on one side, and I can do that with a single query on the other side. This is what we call the quantum speedup. So this was the first observed instance of a quantum speedup. So which is why this is considered to be the first proper quantum algorithm, where I take a classical problem and I show that we cannot, in fact, I can do this in say 2 to the power n by 2 steps. This whole problem can be solved twice as fast, but not any more faster than that. It will still be exponential in n. But when I have a quantum computer, or rather, yes, because right now we don't have a quantum computer that can solve the Deutsch-Jozsa algorithm for arbitrarily large functions. No. If I give you a 100 variable Boolean function, then we probably don't have a quantum computer that can implement the Boolean function, apply the Hadamard gates, and do all these processes. Right now, we don't have it with us. So, but as a proof of concept, we showed that there exists at least one problem on Earth that a quantum computer can do faster than a classical computer. You know what? With this, I think I will take a break for today, and I would like to hear some questions. So now let me go and open up the Q&A tab. Wait, oh no, I opened the chat. Yes, the Q&A tab.
Feel free to drop your queries now.
Please go ahead and ask any questions that you want. Best book for quantum algorithms, especially for. Okay, I will come to this at the end. I will go to the very first question that was asked. Is there any digital device or algorithm which does not involve Boolean functions? Well, if I have any analog processes running in my system, then I cannot represent it as a Boolean function. So, let us say I have something like a SLR camera, not a DSLR, but an SLR camera, and I'm somehow connecting that to a computer to set up some kind of an automated camera, then the algorithm that is running that, acquiring the images, cannot be entirely represented by Boolean functions. Because at some part, my variables are no longer discrete. They become continuous. So whenever I have continuous operations, I cannot represent them by Boolean functions. Even when I have discrete operations, if I have something like a randomized algorithm, then again, I cannot represent it as a single Boolean function. I need multiple Boolean functions, and I need to, do some probability and statistics over there. So that is kind of the situation. So in a digital device, if I'm running a randomized algorithm, if I have a true randomness generator, if I have something clubbed to that, and then I'm performing a randomized process on a classical system, then I cannot always represent it by a Boolean function. So this h subscript 3 means 3 times applying h, or saying applying Hadamard to 3 qubits. Well, we are applying a single Hadamard to each of the 3 qubits. So I hope Saurabh Subhashish's question has been answered through that. So okay, so best book for quantum algorithms. So, I mean, these days there are many books. Okay, I think I will take 5 minutes to slightly introduce myself also, so that you can understand where I'm coming from. So I started studying quantum computing in like the summer of 2010, I guess. Yeah, I think yes. So that this would be 15 years of me studying this subject. And when I gave my first presentation on quantum computing, the people evaluating my presentation were, asking me, do you think any of these things is going to be real? Or, like they were not critically evaluating me. They were essentially asking me if I believed any of these things were real. And at that time, I said, I don't know. It is just something because I started studying quantum computing because I was an electrical engineering bachelor who wanted to study physics. And one of my teachers in IIT Jodhpur said, well, if you want to study physics in an engineering department, why don't you study quantum computing? And I was like, okay, fine, I will study it. So I didn't have any great aspirations or anything. It was just the shortcut for me to study some physics while I was doing my engineering coursework as well. So the books and references that I may, so the reason I mentioned this is the books and references that I may cite are actually pretty old now. So, I haven't had the need to explore any new textbooks over the years. So I will say if we want books and references for quantum gates, I will write it over here in the slide. So for algorithms and stuff, so there are 2 textbooks that I have referred to over the years. So the first is quantum computing, quantum computing and computation and information. So this is, or rather it's information and computation. I keep getting confused with the title. I can actually reach out and pick the copy from the shelf, but I'm too lazy to do that. This is the famous book by Nielsen and Chuang. So this is widely considered to be the standard textbook on the matter, because both Nielsen and Chuang have also had several fundamental contributions to quantum computing itself. And the other book that I read like some 5-6 years down the line is this textbook called Quantum Computing, A Gentle Introduction. So this book is by Eleanor Rieffel, Riffel, and I think Wolfgang Pollack. So this is Rieffel and Pollack. So these are the 2 books that I've used, but I think even Rieffel and Pollack is like 7 years old now, and Nielsen and Chuang has been around like since I think the early 2000s. So it's a 20-year-old book. But after this, there have been several, like dozens, if not hundreds of textbooks. So ultimately, the pick is yours. The reason I'm saying that these are old is they may not have many of the new modern quantum computing techniques or algorithms that are present. But if you want to understand things from the fundamentals, I believe these 2 books are pretty good. And I have never had the need to go outside of these 2 books. So this is to a question from Anant Gade. So could you explain just briefly about the problem that can be solvable only using quantum computing? So I will, just nitpick for a second here. This is from Dasari Raviteja. So the point is there is no such problem that can be solved only using quantum computing. The question, the right phrasing would be, can you explain about a problem that can be solved efficiently? Like, because ultimately, if there is a problem and if it has a solution, then classically I am given infinite time and resources. I can always reach it. The problem is we don't have infinite time and resources. So given a finite amount of time and resources, are there problems that we can solve only using quantum computing? There are some, but to this day, there isn't a single problem where I can say that a classical computer cannot solve it at the same speed or faster. So in fact, in the present day and age, the only proofs that we have is, yes, quantum computing is fast, but we don't have a proof that classical computing will never be able to catch up to it. In fact, even if I come to the one algorithm that I've discussed here, Deutsch-Jozsa, sure, there is no deterministic classical algorithm that will be able to do what Deutsch-Jozsa does. But we don't know if there exists a randomized quantum algorithm that can do the same. We don't know that. Like more investigation is required. So this whole point as to whether there is something that only a quantum computer can solve, that question is actually very deep and an open question. In fact, my supervisor personally argues that no such problem exists. He has his background in Boolean functions, and he's a mathematician, he's an algebraist. So from his input, he says that that shouldn't be the case. If a quantum computer can do that, then there has to exist an equivalent classical method as well. And although I don't entirely agree with him, I see the spirit of his argument. Like, so if somebody claims that there are problems that can only be solved using quantum computing, then they're misrepresenting the fact. Sure, no existing classical algorithm can work as fast as the quantum algorithm. There may be problems like that, but nobody has ever proven that it cannot be done faster at all by any classical algorithm. So that proof is like never present. So then I have Sujal. Oh, we meet again. So why
one request from my side is, if it is possible, can you maybe it's not possible to explain whole algorithm. Like I wanted to go through this Grover search. Can you explain our users in like layman term? Don't go in mathematical part. Like how
sure.
Grover show the
magic, right?
Yeah. Show them the magic of Grovers, like so that
yes. So what I will do is I will take questions for another 5 minutes, and in the last 10 minutes I will walk through the demo of Grovers. Is that fine?
Yeah, sure.
Okay. So why Kate000 won't appear in the balanced function? To Sujal, personally to you, I will tell you this. You have attended the previous course of mine, so we have taught you the algebra of Deutsch-Jozsa algorithm. Work it out and figure it out yourself. Like, it's a good exercise. So that should kind of, give you an idea. So what are the possible? So you are asking for career opportunities in quantum technology. Unfortunately, I'm not the best person to answer this question. You are better off asking people like Sumit and Harsh, because they are out in the world, they're in the industry, they are organizing this program and doing stuff like this. I am more of an academic kind of a person. So what I can tell you is, on the academic side, there is plenty of demand for people who are working in quantum technologies, quantum computing, and lots of things. Like, over the years, I've only seen the number of people entering this field in academia increase as, faculty members or, research scientists and things like that. But if you are looking for a proper, work-like career, then, ask the people here. They should have a significantly better understanding of the market. Okay, so if it is balanced, when it is constant, how is it? Can you please clarify again? Okay, so Mihir Rath has asked how this is the case. See, I'm summing over all possible values of x. So here, by x, I mean like essentially how many ever x values I have. So for the n equal to 3 case, the function has 8 possible values. So since the function has 8 possible values, if it is a constant, it is either always +1 or always -1. So when I add +1 8 times, what will I get? I will get 2 to the power 3, which is 8. If it is -1 always, then I will add -1 all the time, and I will get -2 to the power 3, which is -8. I hope this answers your question. What is the application of the Deutsch-Jozsa algorithm? As I said, this is a very contrived problem. Okay, so there are actually very few. There are some creative ways where you can bend and twist and turn an existing problem to kind of, thrust it into the Deutsch-Jozsa framework. But actually, there aren't very many, distinguishing between constant and balanced function is, in fact, that should be apparent from this case. How many balanced functions can we have? Essentially, I'm asking, if I have a function that is 0 and 1 an equal number of times, how many balanced functions can I have? The answer is, it actually grows exponentially. But no matter how many variables I have, I will always have only 2 constant functions, either all zeros or all ones. So, the set of constant functions is of a constant size. There are only two constant functions, no matter how many other variables I have, because the output is always going to be 0 or 1. Okay, so I can't think of any real world application, but in the realm of mathematics, sure, there are. Oh God, okay, there are some dogs are fighting. Apologize for that. Now what I will do is I will quickly go to the demonstration. Wait. Yeah. Let's do about. I guess these people are very serious about their session time notes. So this QUniverse is a tool that has been developed by the Center for Development of Advanced Computing, or CDAC. So this is a basic framework. It is free to access. So all of you are welcome to, I'll just add the link to this in the chat. You're free to go ahead and make an account over there. Why aren't you pasting? The chat isn't available. Oh wait, I can't type things in chat. Okay, I'll share this link with you somehow. So this is a toolkit that recently I've started using. Okay, so now let us talk about growers for a second. So wait, yes, I have TFT here. So much like Deutsch-Jozsa, growers begins with applying 3 Hadamard gates. Observe, when I apply 3 Hadamard gates, all these probabilities become equal. Everything is 12.5%. And 12.5 is half of 25. 25% is 1 by 4, so this is 1 by 8. So the probability value agrees. Now this TFT gate that I've defined here is essentially what I need to start my grower search. So let me say I'm applying the grower search. Okay. Nothing has changed. In fact, nothing will change. Nothing should change. Now, what does Grover's algorithm do? What Grover's algorithm does is this. I will quickly switch over to my slides and write the problem as I understand it. Because what I have observed is when people state the Grover search algorithm, they try to use very, fancy terms and things like that. But ultimately, the Grover's algorithm is very straightforward. It's actually a Boolean function problem. Given a Boolean function, that evaluates to 1 at only 1 point. Only 1 input point. How many times do we need to query f of x to find out that point? This is the core problem for Grover search algorithm. Like people will say, I have an unsorted database and I'm trying to do some kind of amplitude amplification and so on and so forth. But ultimately it boils down to this. If I have a Boolean function that evaluates to 1, like it has an output 1 at only 1 input point, everywhere else it will give me an output 0. If I have such a function, then how many times do I need to query the function to find out that point? Ideally speaking, we don't know. Like classically, I can query the function one at a time. Like at every point I will ask, let us say I'm even trying to choose randomly. Even if I choose randomly, the probability of me finding that 1 point is 1 by 2 to the power n, because there are 2 to the power n many outputs. So I will quickly write that here. So classically, one would need two to the power n, approximately to the order of 2 to the power n queries to solve this problem. At least this is our understanding. Okay, so over here, let me be very clear. One would need these many queries to solve this problem. Let me say so far. Again, there may be a classical algorithm that does exactly what the quantum algorithm does. But so far, we have not come across it. Nobody has proven that there cannot exist a quantum algorithm. Okay, so a classical algorithm. Nobody has proven that. There exists a quantum algorithm, and luckily the quantum algorithm says that the answer that we are going to get is the minimum answer. Like if I don't know anything about the Boolean function, then I will need a certain number of queries which I'm going to give right now. And more than that, less than that, I cannot do. If I'm given no information at all, other than only this, that it evaluates to 1 at only 1 point. But is there a classical algorithm to perform it using the same number of queries? Right now, the answer is no. But who knows, somebody might discover something in the future. Okay, so this is not like the be all and end all. All right, now let me switch back to the demo. Now, even you don't know where this PFT function is being. This is a Boolean function, by the way. Now, if I remove the header marks, you will see where the one is coming. But let us do the Grover's algorithm and see what is happening. Now, what Grover's algorithm does is the following. Now, this function is 1 at only 1 point. Or if I'm using the y notation, this is -1 at only 1 point. And it is +1 everywhere else. What this algorithm will do is, it will borrow the amplitudes from these points and distribute them to the point where the function is 1. Essentially, it will take a little bit of amplitude from, all the other, like there are 8 points here. Only one of them evaluates to -1. The rest of them evaluates to +1. So it will take the amplitudes of all the +1 states and add it to the -1 state, no matter where it is. So that is the procedure that Grover discovered. And this GG is essentially what let me see if I can expand the size of this. Let me see if I can zoom in, yes. So this quantity GG here is what is called the Grover gate. It's not increasing the size. So let me apply the Grover gate once. As you can see, suddenly 101 becomes very high. But is this as high as we can go? Because right now I have a 78% probability of measuring 101. Can we go higher than this? The answer is actually yes. So I will apply TFT again. See, nothing has changed. The moment I apply Grover gate again, you see, now all the other states have a probability of 0.78 and 101 has a probability of 94.53. So this function TFT that I defined here has 1 at 101 and 0 everywhere else. Alternatively, it has -1 at 101 and +1 everywhere else. Okay. Now let us say I do the Grover's gate one more time. What happens? Let us see. I will apply TFT a third time. Nothing has changed. But when I apply the Grover's gate, you see, I've gone to a worse position. So there is an optimal number. And what was that optimal number? That optimal number was actually this 2. I only had to do it 2 times for a 3-variable function. If the function evaluates to 1 at exactly 1. So the mathematics of this I'm leaving for now. And just to show that this is exactly what is happening, what I will do is but this will not give me state amplitudes. I should have had the 4-qubit implementation. Okay, I will do that the next time. But I hope you can understand this. This is a Boolean function that evaluates to 101. Evaluates to 1 when the input sequence is 101. Otherwise, it will evaluate to 0. Now, I have found that without opening this box. I don't know what the form of TFT was. That is why I made a separate boxed implementation for TFT. And again, how do I achieve it? I achieve it by first applying 3 Hadamard's. So first, I evaluate the function at every point. That is my starting point. See, I need to start from this. And then I can apply the Grover gate and TFT again, and then the Grover gate again to get the final result. Now let me say I'm deleting the Hadamard gates. See, I'm not getting anything meaningful. They're giving me some there's 000 and 101. There's something is happening here. So the Hadamard gate is essentially what gets this process started. In fact, now, if you are still not believing, oh yes, I think I lost my own challenge. The H gate is also called the Hadamard gate. I thought I will try to take one session without saying Hadamard's name. Well, I failed. So, and Hadamard was not somebody who did quantum computing. Jacques Hadamard was a number theorist, and he was a person who worked in combinatorics. So this matrix is known for almost, I think, over a century now. Almost 200 years, people have known this matrix implementation of this, and it is a coincidence that it is also it is a very fortunate coincidence that this gate also has some application in classical quantum computing. Okay, so let me expand this gate. So as you can see, there are 2 Hadamard gates in this also. Now let me open the Grover gate. This is, oh God, why is it falling off? Yeah. You see, the Grover gate has 1, 2, 3, 4, 5, 6, 7, 8. 8 Hadamard gates. So Hadamard gates are everywhere. And without Hadamard gates, this algorithm cannot be performed. So that is why I wanted to start with Deutsch-Jozsa so that I can show the importance of the Hadamard gate and then move on to Grovers. I will try to do a little bit more, if I get a chance next time, I will try to focus a little bit more on Grovers and Bernstein-Mazirani. But, otherwise, I hope this kind of gives you a feel for things. Okay, I think that is all from my side for today. Let me quickly see if there are any more questions. I think there are 1 or 2 more questions, and with that, I think we can end for today.
Yeah, there's